Hello, I'm going to explain matrix multiplication in this video. A matrix is a two-dimensional object of this form. Let's call it A, A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. So we have m rows and we have n columns. It's a two-dimensional object. So this one is called of size m times n. What are the AJs, AI, all these numbers? It could be a real number, could be a complex number, whatever your universal set that you're thinking possible to construct an object like this, of course. This is important. M is the number of the rows and n is the number of the columns. Our aim is to understand how to multiply two matrices. First, we cannot multiply any two matrices. We have a size condition on the matrices to be able to multiply them. And this condition is given by as follows. A, any matrix of the size m by n, and B, another matrix of size p times q. The multiplication A times B can be performed or is defined if n is equal to p. So the number of the columns in the first matrix should be equal to the number of the rows in the second matrix in order to be able to multiply these two matrices. So the columns of A needs to be number of the rows in B. In this moment, I need to remind that the A times B is different from the BA. So matrix multiplication is not commutative. This will be much more clear later on in this video. So I want to do this process is step by step. First, I want to multiply one row and one column. Assume that we have a dimension 4 here. So we have A1, A2, A3, A4. This is one row. So this is one row, but we have 4 columns. And this is a one column. In order to be able to multiply, this number should be equal to that number. So we must have 4 rows. This multiplication will be A1 times B1 plus A2 times B2 plus A3 times B3 plus A4 times B4. So in your eyes, please visualize you're really multiplying the row with the column. Tuck, tuck, plus tuck, tuck, plus tuck, tuck, plus tuck, tuck. This is what you're doing. It's basically the product of this row and with this column. So we must have only one element. So this is 1 by 1 matrix, one element. So the row times to the column, as a shortcut, we can write this AI times BI's, where I is ranging from 1 to the 4. But this could be possible for any n, right? We can choose n much more larger, and the process will be exactly the same. So this is the multiplication of one row and one column. As an example, with the numbers, sometimes for some people it's easier to understand it with the numbers rather than with the abstract notations. So we have 1, 2, 3, 4, just an example, and 2 minus 1, 1, 2. So we have 1 times 2 plus 2 times minus 1 plus 3 times 1 plus 4 times 2. So that's that number. So this one will go. We have 3 here, we have 8 here, so we have 11. So one number, it is just an 11. So multiplication of this row with this column gives us only one element, which is 11. I think this is clear. Let's move on, multiplying one row with the 2 columns. So we have, in order to be able to save the time and the place, so I'm choosing this time a 3-dimensional one, A1, A2, A3. And we have 2 columns, 3 rows for the B matrix. A1 times B11 plus A2 times B21 plus A3 times B31 will give us to this entry, right? And this row with this column will give us this entry. So A11, B12 plus A2 times B22 plus A3 times B32 will be this number. So this is one row, 3 columns. This is 3 rows, 2 columns. So if you eliminate these two, you have 1 and 2. We must have, as a result, multiplication matrix will be 1 row, 2 columns. That's exactly what we found. And also we can express these ones in terms of the rows and column multiplication. Row, column, row, column. So this is row C1, row column 1. This is row column 2. And we can write this in as a sum as well. As we see, this A1, A2, A3 changes, B1 to B2, 1, B3. This indices here is fixed for this term. So what we are having here as a sum is AI, BI1, and here we have AI, BI2. The second indices is fixed for this entry. Okay. As an example, in terms of the numbers, let's do that. 1, 2, 3, minus 1, 1, 2, 0, 1, minus 1. So this times this minus 1 plus 2 minus 3. That's that number. 1 times 0, 0, 2 minus 3, that number. So we have minus 2 and minus 1. We have 2 entries, 2 columns, 1 row. That's exactly what we've done. Okay, now let's do multiplications of 2 rows with 1 columns. So this is the row 1 and this is row 2 and this is a column. So you have 2 rows, 3 columns, and the 3 rows, 1 column. So the result matrix has to be the 2 rows, 1 column, 2 rows, 1 column. This row by this should give us this entry. This row by this should give us this entry. So as before, this is A11 B1, A1 plus A11 B2 plus A13 B3, which is that entry. A21 B1 plus A22 B2 plus A23 B3 will give us this entry. So a shortcut, this is the R1 times C. As we see, these A1, the first indices in A is fixed and the second indices runs. Of course, B changes over. So this is the this shortcut writing as a sum gives us this entry. Here as a sum as well, this is the B2, 2 is fixed, I runs through. So that's the multiplication. Let's practice with the numbers 1, 2, 3, 3, 2, 1, 1 minus 1, 0. So this is 1, minus 2 plus 0. That's the first entry. That's 3 minus 2, 0. That's the second one here. So this one is minus 1. This one is 1. Since we have 2 rows, 3 columns, and 3 rows, 1 column, we have 2 columns, 1 column, 2 rows, 1 column, which is that entry. So we can generalize this. We've seen enough how we can multiply the 2 matrices. So basically, in general, we have 2 general matrices A and B. So A11, A12. So these are the rows is denoted by the first indices and the columns denoted by the second indices in both matrices. In order to be able to multiply these 2 matrices, this number should be equivalent to this number. And the resulting matrix will be M by N, M by Q. That's the resulting matrix. Each entry here, the ij, which is the ith row and the jth column entry, that's how we present it, will be a sum, such that I will be fixed and j will be fixed, but the k will run through from 1 to n. That's how we've seen in the previously in this video. That is the summary of it. If you would like to think of as a rows and a columns vectors, so in the first matrix, we are thinking the first matrix in terms of the rows, and we are focusing on the second matrix in terms of the columns. So the row times the column row times the columns will go to exactly the corresponding place in the multiplication result matrix. So this is row 1 times C1, this is R1 C1, row 1 to C2, this is R1 C2, row 1 to CQ, this is R1 CQ, and that is R2 to C2, that will be that one, R2 to C1, that will be that one, and so on. You can picture it. I think this will help to picture what's going on. Let's multiply two any matrices, 1, 2, 3, minus 1, 1, minus 1. This times this, so this is 1 plus 2 plus 3, that's that entry. This times this, 1 minus 2 plus 3, that's that. This is minus 1 plus 2 plus 3, that's that. And this times this is minus 1 minus 2 plus 3, that's that. And second row, this times this, you have minus 1 plus 1 minus 1. And this one times this, you have minus 1 minus 1 minus 1, right? And then you have this times this. This is minus 1 minus 1 plus 1 plus 1 minus 1. 1, 1, minus 1. And this times this, you have plus 1 minus 1 minus 1. That's that. So we have 2 by 4 matrices of multiplications. If we figure out these numbers, we find 6, 2, 4, that's 0, that's 1, that's minus 3, that's minus, that is 1, that is minus 1. So this is how we multiply two matrices. Matrices make some calculation computationally or algorithmically possible. A glimpse of the usage of the matrix multiplication. Now consider that we want to solve a linear system of equations as below, with m equations and n unknowns, x1, x2, xn. These are m equations, these are the ai's are the real numbers, x1, x2, xn are the unknowns, and b1, b2, bm's are some numbers. So we can express this linear system of equation in terms of a matrices. So this is called a coefficient matrix. Let's get A11, A12, A1, and the coefficients of the unknowns. If we also construct this matrix, and the x1, x2, xn as a column matrix, and this multiplication here, this left-hand side, is equivalent to matrix multiplications of this times the unknown column vector. And the equation says that this is equivalent to the vector b1, b2, bm. So we have here m rows, n columns, and here we have n unknowns, x1, x2, xn. Since we are multiplying, we must have m rows, 1 column, which is the right-hand side of the equation. So this equation is equivalent to matrix multiplications of this form. We can call this coefficient matrix A, and we can view this one as the column vector X, and this one is column vector B. So this linear system of equation can be expressed as Ax is equal to B in terms of the matrix. As we see, this is a much more simpler way to look at a linear system of equations. And this will lead us a systematic solution for the linear system of equations. How to solve a linear system of equations is another subject for other videos. Thank you for watching.